In this video, we're going to find two different volumes formed by revolving this shaded area around two different vertical axes. So the region is in the first quadrant. It's bounded on the left by the circle x squared plus y squared equals 3, so a circle of radius root 3 centered at the origin. On the right by the vertical line x equals root 3, and above by the horizontal line y equals root 3. So we end up with this little area that we then revolve in what I'm calling part A around the y-axis, and in part B around the line x equals 2. The part that I'm calling part A is actually the whole problem from our textbook. I just want to add one more challenging problem to our day, or one more interesting problem to our day, by doing what I'm calling part B. But let's go on and get started by revolving this region around the y-axis. So we revolve that around the y-axis, and what we'll get, if we just revolved this line around, we'd get a cylinder. And so it's like a cylinder with a spherical hole cut through it. So I like to think about it like it's a cup, but the indentation in the cup at the bottom is actually a circle. So let's find the volume there. So our volume will be an integral, and let's see, it's going to be pi times, and this is definitely going to be a washer problem because, well, our solid has a hole in it, and I see a small radius and a large radius. Since I'm revolving around a vertical line and I'm thinking about using washers to find this volume, I'll be integrating with respect to y. And let's see, I'll be integrating from 0 to the square root of 3. All we need to do now is identify our large radius and our small radius. Well, the large radius is always out there to that vertical line, root 3. And the small radius goes out to my circle. So we need to solve our circle equation here for the variable x. And there it is. And we'll pretend that actually fit in there. That's the square root of 3 minus y squared. All right, well, we're squaring things that were under square root, so this is going to behave very nicely. And in fact, so nicely that even those 3's cancel. Right, 3 minus 3, and I end up with just y squared sitting in here. All right, so let's see. Got a pi over 3y cubed when I find the antiderivative evaluated from 0 to root 3. And if I think about cubing root 3, I'll have root 3 times root 3 times root 3. That part's 3, divided by 3, and it cancels, and I just have pi times root 3. And there's the volume that we were looking for in this first part, pi times the square root of 3. Now, I want to find the other volume. I want to find the volume by taking this region and revolving it around the line at x equals 2. This time I'll get a hole through the middle in the shape of a cylinder, and it's like my solid now will have that kind of curve on the outside. If I thought about this part being the bottom, it's like it has a big base and a little top around that hole. All right, so let's see if we can set that one up. I'm going to go on and erase this first problem so that we can use that same picture as guidance. And all the same preliminary things help us out. I still want to think about using washers here. My region still goes from 0 to root 3, pi times a large radius squared minus a small radius squared with respect to y. So I'm revolving around that vertical axis. I'm thinking about my washer stacking up the y-axis. So now all I have to do is think about what the large radius is and what the small radius is. And from before, I know that if I solve this for x, I get 3 minus y squared. So let's see, furthest away from this axis of revolution is the circle. So I need this distance between the circle and the line x equals 2. That's my big radius. Well, that would be 2 minus that thing. And then my little radius is just the distance between the vertical line at root 3 and that axis. So that would be my little radius. And that would be root 3, excuse me, 2 minus root 3. All right. So now that I have a big radius and a little radius, we're ready to plug them in where they go and integrate. All right, we have some arithmetic to get through. I'm going to go on and pull that pi out front. All right, let's multiply all this out. So 2 squared is 4, minus 4 root 3 minus y squared, plus 3 minus y squared. And now I need to square that. 4 minus 4 root 3 plus 3. Still integrating with respect to y, so pardon the formatting there. Now let's see what simplifies. All right, let's see, in this first part I have a 4 and a 3, which add together to give me a 7, minus this part, and still with that y squared. All right, on the next bit, we'll tell you what, let's not use any unnecessary parentheses. Let's just leave that the way it was. We don't need a parenthesis there. Let's go on and distribute through this minus, but after we've added that 3 and a 4 to get 7. So I have a minus 7 plus 4 root 3. So I have a 7 and a minus 7 that are going to cancel. And looking through here, I have a 4 root 3 minus 4 root 3 minus y squared minus y squared. And we're ready to find an antiderivative. And the only intimidating part, I think, is probably this one. And we're going to be very sneaky in the way we integrate that little bit. But for now, let's just see if we can rewrite what we had on that other board here and start working with it. And I'm just going to write some things out and then I'll talk about what I've done. So it doesn't look exactly the way I had it on this other board, but what I'm thinking about is using the addition and subtraction rule for the definite integral. It says I could split that up into 3 integrals, each of which would be multiplied by a pi out front, even if I forgot it there for a minute. And then I factored the 4 out of this one. So what I have here really is the same thing that I have there. And the reason I wanted to do that is because this integral and this integral are very easy to evaluate. And this one's actually the easiest of them all. But I think of, if you're watching this video, that one might be the one you're worried about right now. So let's do these ones on the ends, and we'll come back to this one in just a minute. So let's see, I'd have pi times 4 root 3y evaluated from 0 to root 3 minus whatever that middle one is minus pi times 1/3 y cubed evaluated from 0 to root 3. All right, well, these aren't bad to deal with now. We just plug things in and then we'll combine like terms at the end. Let's go on and evaluate this one. We're going to be very sneaky. So I'm just going to take this bit I'm circling in green and work on it for a minute. So I'm going to go on and drop that 4 pi down here. And as soon as I have a value, I'm just going to multiply it just to fill in the blank. And so what I want to do is just pretend that I was sitting in whatever calculus class I was in when I first met the definite integral. And I want to hope that I recognize x equals the square root of 3 minus y squared as being the right-hand side of a semicircle. The fact that the bounds start at y equals 0 and end at y equal root 3 means I'm only looking at this bit in the first quadrant, which means this definite integral has a value that matches that area. Well, this is a circle with a radius of root 3, and that's just 1/4 of the circle. So 1/4 pi times r squared gives me that area would just be 3 pi fourths. That's one thing to always remember when dealing with the definite integral. Sometimes you can evaluate one just by knowing an area. So now I just need to do some arithmetic and some simplification, and we'll be all done. All right. Let's see, the root 3 comes in there. That's going to be a 12 pi. The 4's cancel in this middle part, a 3 pi squared. And finally here at the end, minus pi times root 3. That is not a very pretty volume, but it is our final answer here. I'm going to get a decimal approximation just because I'm curious. The volume we were looking for is approximately 2.6 cubic units.